Hello, hello. Are you having a good time? Make some noise if you do. All right. Now we're going to transition into the next session, the Linying talks. So this year we received over 100 submissions. So congratulations to those of you who submit your work and have your work accepted to the Odyssey Symposium. Thank you for choosing Odyssey Symposium for showcasing your work. Next, so the scientific community have come together and conducted a very rigorous assessment of all the submissions. It was a really difficult time for us to pick what projects to showcase at the Linying talk. So these are our winners. We choose them because they really demonstrate from a methods perspective, application perspective, or an open science perspective, how we can collectively advance real-world evidence generation. So without further ado, I will turn to our speakers. So let me first introduce Dr. Kathleen Mullen from University of North Carolina at Chapel Hill.
Good afternoon. I'm excited to be here today to present our work on leveraging cross-species data linkage to improve One Health. One Health is a multidisciplinary effort focused on achieving optimal health for people, animals, and the environment. There are significant opportunities for learning across species in a shared environment. For example, companion animals may be sentinels for environmental exposure, and people and their pets suffer from many of the same disease processes, from asthma to zoonotic diseases. However, we really need a mechanism to study the household occurrence and co-occurrence of disease. A useful One Health demonstrator is metabolic syndrome because it's similar in people and in animals. Animals suffer from metabolic-like syndromes that, like the condition in people, is centered around obesity, as demonstrated by the miniature donkeys in this picture here, and also includes features including dyslipidemia, hypertension, and insulin dysregulation. People and animals have the same or similar disease triggers, social determinant of health modifiers, proposed causal pathways, common disease sequelae, as well as potential co-interventions. However, the question remains, how can we explore the causes of metabolic syndrome in a single household? For this, we really need a secure pet-patient registry linking people, their animals, and the environment, which is exactly the goal of this project. Today, I'm going to talk about two specific parts of this project. The first is the data linkage, or putting the household back together again with EHR data linkage. In this part of the study, we asked how many animals and owners can be identified and linked via their EHRs. So for this part of the project, we used data from the Colorado State University Veterinary Teaching Hospital, as well as human EHR data from the UC Health System. As you can see from the map of Colorado, these two institutions are geographically adjacent. A linkage honest broker performed the record linkage using a hybrid approach that was a combination of deterministic and probabilistic methods within a secure research data warehouse, and linked first name, last name, street address, phone number, and email address from the vet EHR, i.e. the owner's information, to the UC Health EHR, i.e. the patient's information. And we knew if we could link these two people, then we could link the person's pet to the person's EHR. Here are some of our input variables. On the left, showing the number of animal owners and the number of animal patients, and on the right, showing the number of human patients. And the results of our linkage showed that we were able to link over 12,000 veterinary EHR pairs. This means that approximately 29% of the veterinary clients or animal owners are patients of the UC Health system. This was very exciting to us and also means that we'll be able to link the vet EHR of that pet to the EHR of its owner. In the second part of the study, we wanted to interrogate the veterinary electronic health record system for metabolic-like syndrome features. We already know that these features exist and are present in the human EHR as well as in the OMOP CDM, but we really wanted to make sure that they were in the vet EHR so that we could see if we could use our metabolic syndrome as a One Health demonstrator and first use case for a pet patient registry. Here we asked, do key indicators of metabolic-like syndrome exist in the veterinary EHR? We use key indicators, some of which are shown on the left and include elevated body condition score, which in animals is similar to body mass index in people. We also looked for terms such as overweight, diabetes, overconditioned, equine metabolic syndrome, etc. We looked for these terms within the veterinary electronic health records for companion animals, and we found, indeed, we could find these terms. In fact, 51% of cats, almost 44% of dogs, and almost 12% of horses had these terms within their veterinary EHR. So in conclusion, this is a lot of fat cats, but also demonstrates that we may use the metabolic-like syndrome and metabolic syndrome as a first use case and One Health demonstrator for our pet patient registry. So in conclusion, based on the positive results of our 2 feasibility studies, we are going ahead and creating the CSU-CU Pet Patient Registry. We also hope that it will be a blueprint for One Health study across other paired, geographically adjacent vet and human medical institutions in the US and across the world. We feel that a pet patient registry is a great way to explore One Health issues from antimicrobial resistance to chronic disease, environmental health, mental health, trauma, and really a whole bunch more diseases potentially. But really we need you, the Odyssey community, and your use cases to make this come to life. I encourage you to visit me at poster number 114 to learn more details and ask more questions. I would like to acknowledge the contributions of our entire team and thank the Odyssey community for the opportunity to present today. Thank you.
Thank you, Katie, for starting the session on time. Good job. You still have 45 seconds left. So just so you know, each speaker has 7 minutes to present. Our next speaker is Joe Swerdel from J&J. Please, Joe.
Hi, folks. I'm a longtime Odyssey Symposium listener and first-time Odyssey Symposium speaker. So today I'm happy to talk about our work comparing probabilistic and rule-based phenotype algorithms for hypotension and angioedema to the experience observed in randomized clinical trials. Here are our disclosures. So rule-based phenotype algorithms are the standard for identifying outcomes in observational data. However, the performance characteristics of the phenotype algorithms, things such as sensitivity and positive predictive value, are often estimated to be low for many phenotypes. Probabilistic phenotype algorithms, those derived from logistic regression models, offer an alternative to the rule-based method. Prior efforts have demonstrated the potential for probabilistic phenotyping as an alternative to rule-based phenotype algorithms. The objective of this study was to develop a methodology for creating probabilistic phenotypes and to show examples of its use in hypotension, low blood pressure, and angioedema, a subcutaneous tissue swelling triggered by an allergic reaction. So here's something you all know. Here's an example of a rule-based phenotype for angioedema, where you might find a code, either an IC9, IC10 for angioedema, and that would be the cohort entry event, and then you set a cohort exit event. This is what a probabilistic phenotype might look like for angioedema. where you have a bunch of covariates that were selected by the regression model, all indicative of the condition, with a weighted beta coefficient. So for instance, you might have things like an angioedema code within there, which got a certain weight, allergic disposition, an emergency room visit. So for rule-based phenotype algorithms, the way you use them is you create the rule-based phenotype algorithm, and then you find subjects during the time at risk in your cohort of interest satisfying the algorithm. For the probabilistic phenotype, you use noisy labeled positive and negative controls to develop a supervised learning probabilistic model using lasso regularized regression. And by positive controls would be people with a high probability of having the condition of interest. Negative controls would be those with a low probability of having the condition of interest. We then applied our model at each appropriate time point during the time at risk for each subject in the cohort of interest. And from there, we selected the highest probability among the different cut points within the time at risk for each subject. Then we have to use a probability cut point, a point where anything above it would be considered somebody with the condition, anything below would be considered without the condition. To evaluate our models, we conducted our work in 5 administrative claims data sets. For the rule-based algorithm, we used a single occurrence of a diagnosis code for hypotension or angioedema. For the probabilistic phenotypes, we developed the probabilistic phenotypes and examined the results using different probability cut points from a range of 0.5 to 0.9. We then estimated the incidence of angioedema and hypotension while on treatment for 7 antihypertensive and 2 anti-diabetic drugs. Using both the rule-based and probabilistic phenotypes, we performed the analysis on 9 new drug user cohorts between 2010 and 2023. For our metrics, we extracted the incidence estimates in 95% confidence intervals from the results from the randomized clinical trials as a basis for comparison. We computed the proportion of incidence estimates for the rule-based and probabilistic algorithms that fell within the 95% confidence intervals for the incidence estimates from the clinical trials. We also assessed the performance characteristics, in this case positive predictive value and sensitivity, of the rule-based and probabilistic phenotypes using the Odyssey 2-Wolf evaluator. So this is some of the results for angioedema. On the left, you can see the 11 clinical studies that we used for 9 different drugs. The black squares indicate the incident estimate that was given from the clinical trials and the 95% confidence intervals. Here we have the results from the probabilistic and rule-based assessment. Those for the probabilistic are in stars. Those for the rule-based are in diamonds. Those that are in green fell within the 95% confidence interval. Those in red fell outside the 95% confidence interval. What we found was for the probabilistic algorithm at a 0.67 cut point that 77% of the estimates from the probabilistic algorithm fell within the 95% confidence interval, while we found for the rule-based 23% fell within the 95% confidence interval. For the performance characteristics, we also found better sensitivity and positive predictive value for the probabilistic over the rule-based algorithm. We found similar results for hypotension, again for a cut point of 0.67, where for the probabilistic algorithm we found a 78% fell within the 95% confidence interval, whereas 11% for the rule-based fell within the 95% confidence interval. For both angioedema and hypotension, the 0.67 cut point provided the closest match for the RCT results. Lower cut points produced higher average incidence estimates compared to RCT results, and higher cut points produced lower average incidence estimates compared to the RCT results. In conclusion then, probabilistic phenotype algorithms for angioedema and hypotension estimated the incidence closer to the results from RCTs compared to those for the rule-based phenotype algorithms. The performance of probabilistic phenotype algorithms was superior to rule-based based on the characteristics of positive predictive value and sensitivity. Future research is still needed to evaluate the performance of probabilistic phenotype algorithms in post-market safety studies and to determine how they could potentially be used to estimate the incidence of drug adverse effects. And thank you. And if you have any questions, please come to poster 115.
Thank you, Joe. Our next speaker is Sujin from Ajou University.
Hi everyone, my name is Sujin and I'm a PhD student at Ajou University. Today I'm going to talk about my research, and the title of my research is Exploring the Interplay Between Metabolic Syndrome and Brain Volume in Depression. Multimodal research has been a key component in medical studies. By integrating data like brain images, clinical records, clinical notes, we can gain a more complete picture for better health research. Alongside this, multi-organ interaction is gaining attention because our organs don't work in isolation. Understanding how the brain, heart, and gut connect give us insights into disease and health that single organ studies might miss. So OMOP-CDM is especially useful in this context. Its standardized format makes integrating diverse types of data more efficient. So there were successful reconstruction cases like radiology CDM and genomic CDM, enhancing the potential for large-scale multimodal research. However, there are still limited use cases, particularly those involving multi-organ interactions. Despite limited research, our research team has been actively making great efforts to bridge this gap. This year, we published two papers demonstrating the power of multimodality by developing prediction models for treatment-resistant depression and suicidal deaths using medical records and clinical notes and brain images. The study that I'm going to present today is also a part of our recent efforts, and this shows how we used OMOP-CDM to explore brain-body interactions in depression and metabolic syndrome. I developed classification models for metabolic syndrome in patients with depression. Depression and metabolic syndrome are closely linked, sharing mechanisms like inflammation and neuroendocrine dysregulation. This suggests a bidirectional relationship where each condition can worsen the other. So despite this, the potential pathophysiological connections between metabolic syndrome and depression haven't been extensively explored. So building on previous findings that the brain may act as a mediator, we investigated brain-body interactions to further understand this connection. So we started this study with these two hypotheses. First, that interactions between brain volume and blood lab variables could explain the link between depression and metabolic syndrome. And second, that these interactions could identify depression subtypes, helping predict their risk for metabolic syndrome. In this study, we followed these three key steps. First, we reduced brain regions using non-negative matrix vectorization, which is called NMF. And then we used canonical correlation analysis to examine the interaction between brain and body using both brain image features and clinical features. Finally, we applied clustering analysis to identify patient subtypes of depression and developed classification models. Using the OMOP-CDM database of Ajou University Hospital, we comprised a study cohort of patients with depression. We excluded patients without brain MRI images, and we excluded patients with those who had previous psychiatric diseases. So after pre-processing, the final sample consisted of two groups, 76 with metabolic syndrome and 74 without metabolic syndrome, respectively. And NMF, which was used to reveal, kick networks within the brain, is a method that determines how brain networks are organized. For the CCA, we use 6 metabolic syndrome variables and 38 blood test features to analyze how these interact with the brain networks identified from NMF. This allowed us to reveal important brain-body interactions that contribute to metabolic syndrome classification. Then, to identify potential subtypes of patients with depression, we used K-means clustering based on the first CCA component. We determined the optimal K by using metrics like Silhouette score, and this resulted in 4 depression subtypes. For classification, we used XGBoost, and 3 models were developed. Model 1 with demographic features and metabolic syndromes, and Model 2 adding more VVM NMF components, and Model 3 incorporate subtype. So through NMF, brain volume was reduced to 4 components, corresponding to previously known structural brain networks. And through CCA, 4 distinct components were identified with loadings corresponding to clinical variables and structural brain networks, which occur to 4 NMF components, respectively. And Model 1 had an AUROC of 68, and while adding NMF components in Model 2, improved it to 72. And Model 3, which includes subtypes, performed the best with an AUROC 75. So across our metrics, Model 3 showed the highest performance. So this is research summary. Our initial exploration of brain-body interactions using CDM was instrumental in understanding the impact of this multi-organ interaction on health. We found that these interactions can be effective classifiers, and we believe there's much potential to apply this approach to other domains and other samples, offering deeper insights into how multi-organ interactions influence health. So thanks for listening, and I'll be really happy to discuss the clinical interpretations of these found brain networks and their roles in the subtypes during the poster session. Thank you.
Thank you, Sujin, for a great presentation, and thank you for flying across the Pacific Ocean to join us here today. Our next speaker is also from outside of the U.S., Edward Byrne from University of Oxford.
Thank you. So I'm going to talk about a new Odyssey R package today called CohortConstructor. So I think as people will have noticed as the morning's gone on, and even some of the previous presentations, cohorts are a key building block in research studies where we define some people who fulfill some criteria for some amount of time. And we already have well-established Odyssey tools for defining cohorts. So we have Atlas, that I'm sure many in the room are familiar with, and also Caper. And behind the scenes, you have the Circe engine that's doing a lot of the work. And these allow us to define cohorts and can be instantiated in a database, and also can be stored in a library for future reuse. However, there are some limitations in the current approach for certain types of studies. So in particular, in certain circumstances, we have computational challenges when making many cohorts. And sometimes we might want to have very bespoke cohort logic that we might not be able to do with the current tools. So that was the motivation for building this package. So first, I'm just going to talk about how it can help make many cohorts at the same time. So in the typical approach, to making cohorts, we define them independently and instantiate them sequentially. So we might have a cohort of asthma, and then we might have another cohort of COPD that we then create, one for diabetes, one for paracetamol, one for warfarin. So CohortConstructor works slightly differently in that it builds cohorts by domain instead of by definition. So say those first 3 cohorts were defined based on the condition occurrence table, so codes in the condition occurrence table. They would all be built at the same time together. And similarly for our drugs, they would also be built simultaneously. So I've taken a risk. Hopefully this will work to see what this looks like in practice. So here we connect to the Eunomia data set. We're going to get some drug ingredient codes. So here we've got 6 drug ingredients that we want to make cohorts for. And then we start with CohortConstructor making a concept cohort. So as you can see, this will build all 6 together because they're all based on the drug domain. And after making these cohorts, you'll have the settings associated with creating them, such as the CDM version, the vocabulary version, and also other attributes like the cohort count. CohortConstructor also kind of facilitates making going from one cohort to many. So we might often in studies build many cohorts that only vary slightly. So we might say have an asthma cohort where we have a requirement of 0 prior days observation and age under 18. We might have another cohort definition that's the only thing we change is that people are required to be 18 or over. And then we might have a couple of sensitivity cohorts where we add the requirement of 365 days prior observation. So with CohortConstructor, it encourages building a base cohort from which these subsequent study cohorts can be derived. So in this approach, you'd build your asthma base cohort, and then you'd apply the requirements about prior observations, and you get 2 cohorts back. And then you'd apply the age criteria, you get 4 cohorts back, and you'd end up in the same place as before. Again, we can see what this looks like. So working with those same 6 drug cohorts we started with, we can just add a requirement about 2 prior observations. This will give us 12 cohorts back, where they vary based on that requirement. We can then also apply 2 requirements about age, and then we'll get to 24 cohorts where we have both that variation in prior observation requirements and age. And again, we'll track the settings associated with those cohorts and the counts of them. So under this approach, you often end up with programmatic pipelines to build these cohorts. So what that needs is lots of utility functions to kind of facilitate doing kind of whatever you can think of to your cohort. These functions include adding or subtracting days to cohort entry and exit, creating cohorts based on age. So for example, creating a cohort of people that enter on their 18th birthday, resetting entry and exit to the cohort based on some external date variables you might have, requiring subjects are present in or absent from another cohort or a table in the OMOP CDM in some time window, taking random samples of cohorts, and also persisting cohort entry across multiple observation periods, and that'll be in the next release. So what might this look like? So here, for example, we define a hip fracture. We start with the exit at the same day as the event. We then reset that to be 180 days afterwards. We require that it's a first entry. And then just to show how it looks like, we take a sample of the cohort. So the maximum cohort will have at most 100 people. Again, we'll have the settings and counts associated with our cohorts we create. As part of the process of building this package, we're working on some benchmarking. It's still very much a work in progress. To start with, we've taken 9 cohorts from the Odyssey phenotype library. Firstly, we've created these cohorts using Circe and then also with CohortConstructor. If it was on the dotted line, that would mean they take exactly the same time. As you can see in these test databases, CohortConstructor is actually a bit slower, which maybe I shouldn't have shown this one. But once we start working with real data, we see some differences. So here we have one data set from Estonia with around 400,000 people, and CPRD Aurum from the UK with close to 50 million people. Here we're no longer looking at minutes on the axis, but hours, and it's on the log scale. So we can see, in general, making a single cohort takes about the same amount of time. except for one of the cohorts we found that it was taking nearly 100 hours to make using current tools, and with CohortConstructor it was done in an hour. So that's it. I've tried to sell it with that last example. I'm sure others could be found. Yeah, so just to wrap up, here's some more information. So there's a website to go with the package. There's a GitHub link to Odyssey. There's also benchmarking code, so it'd be great if data partners in the room wanted to give it a go and give some feedback. And if people have examples of cohorts they want to build, they could try it out. And just lastly, to thank the other contributors to the package who've done a lot of the work, and also the data partners that have run the benchmarking so far. And I think with that, I'll just say thank you.
Thank you, Edward. We're halfway through. How are you doing? Do you like the talks? Make some noise if you do. All right. So our next speaker is Jiayi Tong from Johns Hopkins University.
Thanks for the introduction. Hello, everyone. Good afternoon. And today, I'm very excited to share our work on unlocking the efficiency in real-world collaborative studies through a multi-site international study with COLA-GLMM. First, I would like to thank the efforts made by the Odyssey community with over 3,000 collaborators across the whole world, and the number now increased to 4,000, as George introduced this morning. And a significant amount of real-world data have been leveraged to use to generate a robust and real-world evidence. And more importantly, these efforts facilitate open science by promoting more and more international studies. However, one of the primary challenges in international study is the inability to share individual patient-level data across different sites. And the time-consuming regulatory approvals process and the diverse laws across different countries make the international study really complicated. And under such context, the privacy-preserving federated learning algorithms become very important. And these algorithms enable fitting the statistical model in a distributed manner and only require the sharing of summary-level statistics instead of the patient-level data. And such feature can ensure the data privacy and security. A remarkable thing is that within the Odyssey Research Network, a large number of federated learning algorithms have been successfully implemented. For example, distributed linear mixed model, also termed as DLMM, has been applied to analyze the data from 11 databases from 3 different countries. And the objective of this study was to investigate the association between the demographic and clinical characteristic with the continuous outcome, which is the length of hospital stay for COVID-19 patients. And for this DLMM algorithm, it has 2 ideal properties for federated learning algorithms. The first property is called lossless, which means that the results by using federated learning algorithms would be identical to those by using the pooled analysis. It means that there is no accuracy loss due to the data sharing constraints. And the second property is called one-shot, which means that when we implement the federated learning algorithms in a practical setting, only a single round of communication is needed. And to date, only a few algorithms have successfully achieved both lossless and one-shot properties. One is linear regression model, and the other is the linear mixed model that I just introduced. However, given the diverse nature of real-world data, there are other types of outcomes available beyond continuous outcome. And also, when we do multi-site analysis, the between-site heterogeneity problem is the key consideration. So it is very important for us to develop the federated learning algorithm for generalized linear mixed model. And efforts have been made along this line of research, but given the complexity of the real-world data and also the nonlinearity of the estimating functions, the existing methods are not able to achieve both lossless and one-shot features. And here today, I would like to introduce our new method, COLA-GLMM. And COLA-GLMM stands for Collaborative One-Shot Lossless Algorithm for Generalized Linear Mixed Model. And this CohortGLMM algorithm operates under the assumption that a common set of covariates should be available at all collaborating sites, and these variables should be standardized into categorical variables. And the pipeline of CohortGLMM is that for each collaborating site, they will use their own patient-level data to generate some summary-level statistics. For example, we have the patient-level data have two covariates, one indicator for female and one indicator for age larger than 65. And we're interested in a binary outcome. And here, the generated summary-level statistics include, first, all possible combinations for the two covariates. And then we're going to count the number of patients matching the unique combination. And also, we're going to calculate the sum of outcome values and the sum of outcomes times the covariates for each unique combinations. And this procedure will be done independently and in parallel within each collaborating site, and the summary-level statistics will be transferred to the coordinating center for feeding GLMM model so that we can estimate a parameter of interest, for example, the fixed effect and the random effect. To demonstrate the performance of our CohortGLMM, we have run some simulation studies. And we first compared the pooled analysis with the most commonly used method for evidence synthesis, which is the meta-analysis method. And when we try to simulate the setting, there exists some level of heterogeneous set level of random effects. From this figure, you can see the meta-analysis method cannot have very accurate results compared with the pooled analysis. And then we compare our method, CohortGLMM, with the pooled analysis. And then from this figure, you can see the results show the lossless property of CohortGLMM, which means our method can produce exactly the same as the pooled analysis in estimating the fixed effect. We also consider a practical concern related to the risk of re-identification problem when there is a small cells issue. And here we follow the CMS cell suppression policy, and you can see our method is robust enough to provide similar results as the pooled analysis. And we apply our method to the real-world setting, and we aim to identify the COVID-19 mortality risk factors. And we also want to check the consistency of these significant risk factors. And we collaborated with 8 different data partners across 3 different countries within the Odyssey Research Network. And finally, we found sex, the Charlson Comorbidity Index, and age consistently emerge as the significant risk factors for COVID-19 mortality. To summarize, here we propose CohortGLMM, which is a lossless, one-shot, and privacy-preserving algorithm. And it is able to handle the between-set heterogeneity. And more importantly, our CohortGLMM is applicable and ready for implementation within the Odyssey Research Network. And finally, I want to thank all of the data partners and our collaborators. If you have any questions, please feel free to solve them in poster 117. Thank you very much.
Thanks, Jessie. I just love that acronym, COLA for model. I think yesterday I heard an acronym for a different model, although from the same lab, called a latte. I think they are ready for a drinking party sometime soon, so keep your eye out for that. And our next speaker, Zhang from University of Pennsylvania. Welcome, Zhang.
Good afternoon, everyone. My name is Zhang. I'm a 4th-year PhD student in biostatistics from UPenn. And today my topic is about NCO calibrated DID analysis. So let's first go over a real-world case study. And we know the racial ethnic disparities have been long-lasting in the healthcare. And when the pandemic comes, a paper published talk about the COVID-19 association with the racial ethnic disparities. And a more important research question would be, does the pandemic worsen the racial ethnic disparities? To answer this question, a difference in difference approach can help find the racial ethnic disparities attributable to the pandemic, while controlling from the pre-existing disparities. And here the picture shows how it works. So first, the red line showed the prevalence of outcome for the minority racial group, and the blue line showed the non-Hispanic white group, and the purple area would be the racial ethnic differences after the COVID-19 infection. Similarly, the difference can help identify the pre-existing racial disparities shown in this picture as gray area. So in this way, the difference or DID can help identify the racial ethnic difference attributed to the COVID-19 infection. However, it has a key assumption, which named the parallel trains assumption. And the parallel trains assumption stated that in the absence of the intervention, the before intervention difference and the after intervention difference should be the same. And this means that in the plot, the green area before and after is equal to the counterfactual outcome differences. However, in the reality, this may not be scientified, and because of the system bias from the unmeasured confounding variables. And here's the picture show the real scenario. So the system bias shown in the gray area, it is not identified. And thus, we cannot use the difference analysis to identify the racial ethnic difference attributable to COVID-19 infection. And how to calculate it? So you guys may already heard the legend this morning. And so the legend used the empirical calibration. And here's the landmark paper on the PNAS. And it used the negative control outcome. And it is known in priori to be unrelated to the exposure. And the legend study, for example, used the ingronel as one NCO that is known to be unrelated to the anterior hypotension. And a recent published paper from our group, we used the Odyssey framework to calibrate the symptom bias. And here's the example of the 40 NCOs. And here's the list of all the NCOs. So our question is that, can we make an empirical calibration for the DID model? And here's our proposed method, NCO DID. So in the step 1, we used a DID model on the cohort by using the outcome of interest as the outcome. And the beta 3 would be the parameter of interest. And step 2, we fit the DID model for an NCO. And step 3 would be empirical calibrate. So from this proposed method, you may ask the question, why the estimation from the DID model for an NCO is equivalent to the estimation for the symptom bias? And here's the reason. So we can write down an estimating equation for the outcome of interest, and it has 2 parts. The first part would be the symptom bias for the outcome of interest, and the beta 3 would be the true effect size. And similarly, we can write down the estimating function for the NCO, and it also has 2 parts. It would be the system bias for the NCO plus the true effect size. And we know because of the NCO, the true effect size should be 0. And we also make assumption that the system bias for the NCO is equal to the systematic bias for the outcome of interest. So that we have this equation. That is, estimation of our 3 hat is approximately equal to the system bias for the outcome of interest. And in this way, we're able to calibrate the system bias. And in reality, we leverage M NCOs, just like the example I showed you for 40 NCOs for the vaccine study. And here's the comparison. So the baseline method would be the traditional DID model. And our proposed method, we have one more step to use the empirical calibration. And here we made an empirical evaluation from different sample sets from 1,000 to 3,000. And the before calibration, the gray box plot showed the traditional DID model, and the orange box plot showed the proposed method. So you can see that across all the scenarios, the proposed method can have a smaller bias to the true effect size, and also it has a better coverage probability. So our key message is that across all the scenarios, the proposed NCO DID model successfully calibrates the systematic bias. And for the real-world case study, it is now under revision at the Nature Communications. So our takeaway message is that, first, we extend the Odyssey empirical calibration framework for the DID model. And secondly, it helps to control the cinema bias from the unmeasured confounding variables. And third, in the real-world case study, it helps to understand the racial ethnic difference in long COVID conditions after COVID-19 infection. And here's my acknowledgement. My poster would be number 118, and you are welcome to ask questions. And the first QR code is for my code, and the second QR code is for my Google Scholar page. So if you have any questions, you can feel free to email me. And by the way, I'm on the job market, so if you have any questions, you can also feel free to email me. Okay, thank you.
Thanks, Zhang, and good luck on your job application. I was in that same shoes 2 years ago and made that same comment. Our next speaker is Sam Patno from Health Partners Institute.
Thanks for the opportunity to talk about the health trends across communities in Minnesota project today. My name is Sam Patno. I'm an informatics programmer at Health Partners Institute, and today I'm presenting on behalf of the Minnesota EHR Consortium, which led this work in partnership with Hennepin County, the Center for Community Health, and with funding from the Minnesota Department of Health. So first, I want to give some background on the Minnesota EHR Consortium. It was formed in March 2020 in response to COVID-19. It includes researchers, state agencies, and the 11 largest health systems in Minnesota. Some of those systems are shown here on the screen on the right. These systems cover all regions of the state and provide care to over 90% of Minnesota residents. The consortium uses a federated data model, and in 2022 began a coordinated adoption of the OMOP CDM across all the health systems. Health trends across communities in Minnesota, also called HTAC Minnesota, began in 2023 as the first project to fully leverage the OMOP CDM across the consortium, with the goal of building a comprehensive statewide dashboard that could support public health surveillance, inform community health assessments, and promote health equity across the state. The HTAC Minnesota dashboard was released earlier this year and made publicly available at the link shown here in March. The dashboard includes prevalence estimates for over 30 health conditions. In the next slide, I'll talk about what those conditions are, how they were defined and selected. The denominator for 2022, as shown here on this screen, was over 5.4 million people, roughly 93% of the estimated state population. That denominator includes patients who received care at any of the health systems in the consortium within the prior 3 years, and prevalence estimates on the dashboard represent patients who received a diagnosis for any of the given conditions in the prior 5 years. This example is showing prevalence for asthma. Here you'll see that the dashboard has data by race, ethnicity, age, and sex. By geography, you can look at the dashboard and find data at the state level, or you can filter by region, county, and then go all the way down to the census tract level. And that was made possible because each of the health systems in the consortium added a census tract field to their location table. This image here shows an example of hypertension prevalence for one census tract in Minneapolis. The teal bars on the right show the prevalence of hypertension for the selected census tract compared to the overall rates shown for across the whole state of Minnesota, shown in the light blue charts there. The dashboard has data for the years 2020 through 2023, and it's much more timely than typical health survey data as it's refreshed annually. 2024 data should be available on the dashboard as soon as March 2025. So the process for selecting and defining health conditions for the dashboard included 3 main steps. First, the Minnesota EHR Consortium worked with the Center for Community Health to identify and prioritize health conditions for the dashboard, following the criteria listed here. That process led to the selected health conditions listed here. There are 31 of them currently, and they fall under a bunch of different domains. My favorite domain is Other, that captures everything. And then finally, from those selected health conditions, the Minnesota EHR Consortium worked with analysts and subject matter experts across the consortium to develop standardized OMOP concept sets for each of those conditions. These are mostly mapped from ICD-10 diagnostic code sets and existing algorithms, and they include the SNOMED and ICD concept mappings. They also account for metadata across the consortium health systems. They're reviewed by clinicians for validity, and each condition is defined uniformly across all the health systems and centrally managed. So now that you've seen a preview of the dashboard and have a better understanding of how the conditions were defined and selected, I'm giving you a look under the hood to see the engine that kind of runs the whole thing and makes sure it goes smoothly. A central part of that engine are the red boxes you see here, representing each health system's OMOP common data model. 2 customizations that were made for the Minnesota EHR sites included adding a census tract column to the location table, which I mentioned earlier, and then creating an observation 2 table to store flags for external data, the external data flags and deduplication. Deduplication was an important part of this project to avoid the overestimation of prevalence for conditions. So now I'm going to give you a closer look from the health system perspective to explain how that process works. So now we're zooming in on that last visual and now looking at the health system perspective. I'll show you how this process works. Hopefully the animations work as well. So the first step is that each system sends de-identified patient level file with deduplication information for their patient population to an encrypted data shelter using one-way encryption. From there, in the encrypted data shelter, patient level files are deduplicated and linked to external data using privacy-preserving hashing functions. And here this external data is represented by this green box that's coming from state programs. From there, a matched, encrypted, deduplicated person-level file is returned to each health system, and that's used for populating the observation 2 table with deduplication and external flags. So how this works is that if a patient is seen at 2 or more health systems within the consortium, they'll only be counted at the one that has complete race data, the most blood pressure measurements in the last 12 or 36 months, and the most recent year of a diagnosis. From there, since all the systems are using OMOP CDM, a single set of R code for generating summary data is sent to all the systems. That's run and creates a summary data file for each health system, represented here by this blue box. And then from there, those summaries are combined centrally and aggregated into the data file that becomes the source for the Power BI dashboard. In conclusion, the HTAC Minnesota dashboard demonstrates how OMOP can facilitate sharing summary EHR data across an entire state to monitor community health. For more information, please visit me at poster 119 in the Garden State Room right after this. You can scan this QR code. I don't know if it works from this distance, but it's pretty big, so you can try. And there's tons of great information on this website. There's condition descriptions, a glossary of terms, and an FAQ section. So please check it out and come talk to me with any questions, concerns, or compliments at the poster session right after this. Thanks for your time.
Last but not least, our speaker is Cindy Chen from Columbia University.
Hi, everyone. Oh no, hold on. This is what happens when they don't give us presenter mode. Okay. Yeah, this is good, I think. Can everyone hear me? Excellent. So this is How Often, which is a project that we kind of worked on all together last year at the symposium. Well, this is one of the projects. So incidence rate calculation is one of the most common analyses in pharmacoepidemiology, whether it is used for comparative background rates for drug adverse events, assessing the potential impact of adverse events, or designing clinical trials. Here I just have the definition, and it's defined as the ratio of the number of cases to the total time at risk for patients in the target cohort. So why incidence rate? Well, first off, calculating incidence rates is relatively simple, and it has fewer assumptions. And while incidence rates are more used for characterization, and rates themselves are not meant to be interpreted from a causal perspective, it can still be really useful. So here I just have an example. If we know that the incidence rates are low and the side effect is not serious, then we probably don't need to worry so much about that. But on the other hand, if the incidence rate is high, then we probably still need to look out for that outcome, whether or not it's caused by the drug itself. So I said it's simple, but it still can be relatively complex. Previous Odyssey works have demonstrated that different factors like age, anchoring, database, and biological sex can influence incidence rate up to 1,000-fold. So we know that incidence rate estimates are sensitive to factors like age, sex, calendar time, and database. So the next question that we had was, does indication matter when it comes to estimating incidence rates? Well, we kind of do know the answer. And a really obvious example is if someone is taking a beta blocker because of a previous heart attack, then of course their incidence rate for heart attack after taking the beta blocker for that specific population is also going to just be higher. Now, what we don't know is what the extent of that variation is when we measure incidence rates by different indications. In addition, we're also interested in the relative contribution of drug indication to heterogeneity in these incidence rate estimates, and we want to compare that relative contribution to age, biological sex, and database. So, as I mentioned, how often is our effort to characterize incidence of outcomes following drug exposure? And this was kind of started as a community effort last year. So we had different community calls in June and August to detail different aspects of this effort. We put out a call to the Odyssey community to get different research questions and develop a phenotype or develop phenotypes and draft a protocol. And if you were here last year at the Symposium, we actually ran a full day How Often workshop. We had all of our data partners execute the How Often analysis package. We had lots of good discussions. And this is just one of many projects that resulted from the Symposium last year. So going into more detail about the methods of our specific project, which looked at indications, we conducted the analysis on 13 different databases in October 2023, and obviously this was done last year during the Symposium, as I mentioned. For the study design, the target cohorts are based on the first occurrence of a drug exposure in a patient's longitudinal record. We have 12 different drug classes, and each drug class was also further separated into different indications. Our outcome cohorts were 73 different outcomes, and they were developed by the Odyssey community, and they can all actually be found in the phenotype library. And I'll give examples of both the target and outcome cohorts in a second. Our time at risk is 1 day to a year after the cohort start. We stratified by age and gender, and for each of these outcome pairs, we calculated the incidence rate. And this is the 12 different drug classes. There is a typo on here. It's supposed to say GLP-1 agonists, but 8 of these drug classes had 2 or more indications, and 6 of them had exactly 2 indications. Beta blockers had 3 indications, and then TNF-alpha inhibitors had 5 different indications. And then here's like a little sampling of the outcomes that we looked at. As I said, there's 73 total, so I just kind of pick and chose a couple from 3 different systems, but this is not an exhaustive list by any means. And then for analysis, we conducted a random effect meta-analysis of incidence rates across 13 different databases. We compared the difference in indications with a random effects model, and then we used variance components to quantify the relative heterogeneity between age, sex, database, and drug indication. And all of this was done in R using the Meta4 package. For our results, we had a total of 77,000 incidence rates that were calculated. And as I mentioned, 8 different drug classes had at least 2 indications. And then here on the rightmost column, you'll see the median variance component for each drug class. What this means is that for each drug outcome pair in that class, we calculated a variance component, and this is the median across all 73 different outcomes. And what this number tells us is how much heterogeneity can be attributed to the indication differences. In other words, if a drug class has high median variance component, the heterogeneity that can be attributed to indications is higher. And here we see that the drug class with the highest variation by indication is trimethoprim, and the drug class with the lowest variation by indication is GLP-1 agonists. And how do the variance components for indication compare to variance components for age, database, and sex? Here we show that usually either database or age have the highest median variance component, followed usually by indication, then biological sex. And the fact that biological sex usually had the smallest variance components is consistent with our previous studies that gender matters a little bit less when it comes to these variations that we see in incidence rate estimations. So some of the key takeaway and next steps. So among the drug classes that we looked at, trimethoprim is the drug class that is most sensitive to indication, and GLP-1s is the drug class that is least sensitive. And then for our variance components analysis, we found that indications contribute less to heterogeneity than database and age, but more so than biological sex. And we've actually been talking about this for a while, but the dream, but most importantly, my advisor, George Hripsack's dream, is to be able to scale up these incidence rate calculations to include all drugs and all outcomes. So you'll definitely be hearing from me and the team about how we can all work together to make this dream happen in the future. And my poster will be 120. Thank you.
Thank you to all speakers for your great presentations. Before I let you go, I have a few logistics items to tell you. So all the Linying talk posters will be in the room right outside of those doors, along with posters for open source analytics, community engagement research, and software demos. But we also have posters for clinical applications and methods research in the room downstairs. So if you go through those doors, take a left, walk down the stairs, you will find that poster room. So I encourage you to go talk to our presenters, ask them questions, and give them feedback. And please make sure, so the next 2 hours, you have the next 2 hours to do that, but please make sure to come back at 5 p.m. for Patrick's fabulous closing remark. Now you're free to go.